Hey AP, Mr. McLeod here. I made a big mistake. It turns out the reason we're getting the wrong answer over and over and over again is because I've been stuck in space when it comes to the way I've been thinking about everything. And what I mean by that is we do actually need the mass for the stopper. This has been racking my brain for days. So used to problems I don't need it, but in this situation we do need the stopper for our little for our lab, for our little spinny lab, this tangled mess here. So, and it took me a little while to figure it out, right? So this is still true. The force of gravity is still equal to the centripetal force. The downward force pulling through the straw is still equal to the horizontal force. But because our perspective is on this side, the cork as it's going around, and the perspective on this side is the mass pulling down, we actually do need to consider the mass of the stopper. Most of us have not measured our stoppers, so my thought process is let's just get a weight for all the stoppers, being that there's only like 4 different ones we could have really picked from that were going around. Remember, this MS is that stopper that's going around. Okay, if I plug in the values that we had earlier, when I was doing my demo in the class, I've looked at the video a bunch of times, but basically we have 0.1 kilograms for the mass times 9.81 for gravity. Okay, and then I just weighed the mass of the stopper I was using, and it was 0.0145 kilograms. And then if we bring in our velocity squared divided by radius, if you guys remember earlier, the radius was 0.37, and the velocity squared ended up being about 25.14. This is for that first trial I did with the straw before we switched to the tube, but it ends up being pretty close. Now, if I then see if this side is in fact equal to that side, what we get is 0.1 times 9.81 gives us about 0.981. 0.981. And then on this side, if we mix it up and we do 0.0145 times 25.14, and we divide that by our time, 0.37, we get we get 0.985. Very, very, very close to the same value. So if we keep this mass in here, I still want you to do that graph we were talking about, that graph with the slope. But to isolate radius now, we got to do a couple extra steps. We got to move this mass over here to the denominator, mass S, and then we have to move this velocity to the denominator, velocity squared. So it's the same thing we were doing before, where we were saying the force over velocity squared, but now we've added the mass down here. And what does that give us? Well, that gives us 1 over r. And once again, if we flip this value, it should be, I'm going to use a marker that actually we can see, we're going to end up with mv squared over r, mv squared over force of gravity is equal to radius. If we graph this being our y, and this being our x, the slope should equal that radius that we calculated earlier. And hopefully I showed that to you a moment ago when I showed you that the force of gravity, in fact, is equal to the centripetal force. Sorry about the confusion. That's been a long-winded thing. Hopefully you will never forget it, and I will definitely never forget it, having gone through this process. Anyway, hopefully the snow hasn't delayed us too long and you guys could fix your labs. Anyway, have a great day.